Okay, guys. One of my students has given me this problem, and so I thought I would use it to explain some of the properties of exponential functions when it comes to derivatives. So what we've got here is we've got the rate at which numbers of bacteria are increasing over time is in a wound is proportional to the number present. This can be modeled by the formula dn dt, or the change in numbers over the change in time, is equal to 0.29n. There are initially 90,000 bacteria present. Find a formula that models the total number of bacteria present. Okay, so the first thing we're going to do is we're going to start with basically I thought I'd start with a completely different example so I could demonstrate one of the properties of a exponential function. So if we have a function, we'll call it f of x, and it's going to be equal to, off the top of my head, let's just say 6e to the 4x. Okay, so if we were to differentiate this, the derivative of an exponential function is itself. That's one of the features. And because of the function inside here, we use the chain rule. So then we times it by the derivative of the inside function, which is 4. So this is going to be 4 times 6e to the 4x. So once we've done that, you can see that the derivative is quite similar to the actual function. So this is the derivative, that's supposed to be a line. So what we can also write, we can write the derivative as, so f prime of x is equal to 4 times the actual function of x, because this is that thing there. So I can write 4 times f of x. So you can see where this relationship lies. The number that we're going to be multiplying by the actual function is the coefficient in front of the variable power in the exponential function. So if we get back to the question that we're being asked to solve, we'll start with A. There are initially 90,000 bacteria present. Find a formula that models the total number of bacteria present. Okay, so using this little relationship that we've come up with, or we've derived here, what we can see is that the coefficient in front of the variable is going to be 0.29. So you've got the function n is going to have to be equal to some initial term, we'll call it n naught to start with, times e to the 0.29 t. Cool. Now it says there are initially, now when it says initially, basically what that means is t equals 0. So at t equals 0 there are 90,000 bacteria. So therefore our n naught is going to be equal to 90,000. So what we do is let's just replace that. So we've got n, the number, is equal to 90,000 times e to the 0.29 t. Okay. How many bacteria are present after 6 hours? Well, basically, okay, let's just make a bit of a separation. B. How many bacteria are present after 6 hours? Well, this is just going to be n, 6, which is equal to 90,000 times e to the 0.29, and instead of t, we write 6. And that gives us, calculator, 512,761. 512,761. 761 bacteria. Cool, so that's not a very complicated question. And it says here, at what rate are the bacteria increasing after 6 hours? So what we can do is we're looking for dn dt evaluated when t equals 6. Now, if we take a glance up to the top here, it says here that dn dt is equal to 0.29 times n. So what we can do here is this is going to be equal to 0.29 times n of 6, which is what we have from, which makes it a bit easier because that's what we have from up here. That's n of 6. And we can double check that in the question. It says the number of bacteria increasing over time in a wound is proportional to the number present. So n of 6 is the number present at t equals 6. So, and the proportionality constant is this 0.29. So we then just go 0.29 times 512,761, and we get a number of 148,700. Now let me just check that. Just the number seems weird to me. 761 times 0.29. Yep, okay, cool. Now, and that's going to be bacteria per hour. Always good to put your units in, guys. Just remember that. Makes you look like you know what you're talking about. So, in D, what is the rate at which the bacteria are increasing after 10 hours? So basically what D is asking us to do is it's asking us to do exactly the same thing as we did in B and C. So first of all, we have to work out what the actual number of bacteria are at 10 hours, and then we just multiply it by 0.29. So what we're going to do, to start with, we're going to find n of 10, which is equal to 90,000 times e to the 0.29 times 10. And that is 1, 6, 3, 5, 6, 7 bacteria. And then we have to go the rate at which, so with dn dt evaluated when t is equal to 10 is going to be equal to 0.29 times 1635673, and that gives us a number of 474,345 bacteria per hour. So you can see that it's not a very complicated question. It's just understanding this relationship between an exponential function's derivative and the exponential function that the derivative is taken from. So, if you go through a problem like this by yourself, just ensure that when you have the rate of change formula like we were given here, all you must do is just this number here is going to be the coefficient of the variable that's in the power of the if it's an exponential function. Usually it will have to be an exponential function because it's the only function where the rate is proportional to the actual number present. So yeah, I hope this video helped, and I'll see you again next time.